Welcome everybody on Zoom. Welcome everybody in the lecture hall. Today we are going to hopefully finish MapReduce that we started last week. And then we are, the microphone is not good? Yeah, that's what I was kind of worried about. Let me see if I increase here and if I increase there. Is it better now? A bit better? Even higher, like this? Like this, it works. Okay. Okay, great. So I was saying that last week we started with MapReduce, and today we are going to continue and hopefully finish. And if time permits, we are going to look at how it was improved, because there was a second generation of improvements, MapReduce v1 versus MapReduce v2. And then we look into the next generation, parallel processing, because there's something more modern than MapReduce. But understanding MapReduce is very important to understand the more modern mechanisms, because this is really a generalization. Before we continue with MapReduce, I have a question for you, clicker question that I will open now. Okay, here you go. So this is to make sure that you have the right intuition on MapReduce. So imagine that you have a cluster, 1,000 machines, and you've submitted a job there on these 1,000 machines. So of course, I'm assuming that you picked the 1,000 machines based on what your job needs, right? So you submit your job. What do you do next? Do you have the results right ahead? You don't need to even wait, it's interactive. Answer number 2, you go for a cup of coffee. And after a few minutes, it's done. Or you switch to something else completely and check again in a few hours, even tomorrow. Or you hide from the CFO. Ah, interesting. Is the majority correct? You can still change your answer. All right. And this is the correct answer. Oh, somebody changed their mind in the last minutes with us, you. All right, so yes, indeed, it takes a lot of time. When you have 1,000 machines, it's not the sort of things that, happens very quickly. Because when you set up the machine for the MapReduce job, the cluster, you need to take into account all the time that it needs to prepare every environment on every machine right until they are all done, then starting the jobs and the tasks, the shuffling. Can you imagine what it's going to be? So it takes a lot of time. So typically, when you have a job at that scale, you typically are talking about enormous quantities of data, and you typically let it run and come back on the following day, right, overnight. And if you're lucky, it will have succeeded. If you're unlucky, then it will have failed, and you need to start again, right? So this is just to communicate this intuition that if you are looking at a scale of 1,000 nodes, this is about several hours. You might have something within a few minutes if it's smaller, right? If you have, let's say, 4 or 5 machines and you're querying maybe a few, I don't know, tens of gigabytes, hundreds of gigabytes, a terabyte, maybe this is going to be done in a few minutes. Interactive, almost no way. This is the reason why, if this is really not much data, it's much quicker to do it on your laptop. In many cases, it's going to be faster on a single machine. So you really need to question whenever you go to a cluster, whether the fixed cost of actually going there and setting up the machines is worth it, or if it's not better to write some good code on your computer. And this is really an advice that would be useful to many people creating a new startup who want to deal with data, because it's very tempting to go to a cluster but the truth is you can already achieve a lot with a single machine. You save costs, it's cheaper, and it's going to be faster. Forces you to squeeze your data into less space to find an efficient format, way of storing it. Forces you to write good code that that is efficient, that doesn't do useless things like reading useless columns from the data and so on. All right. And we obviously have 6 people who have experience working in a company and who know exactly what to do when, especially if they forgot to delete the cluster. That can have consequences. Okay, in the case of the cluster, so we will have an exercise on the cluster a bit later, probably in December or so. And here, you're kind of safe because you're in a safe environment where we grant you an amount of money and then it runs out of money. But of course, it's a good exercise for you to apply to not forget to switch off your cluster once you're done with it. All right, so now I'm going back to the slides. This was this. All right. So let's start right from where we were. Remember that MapReduce is a framework. It's low level. It doesn't know about data being tables or anything, about trees. It doesn't know everything is a collection of key value pairs, right? Everything is a collection of key value pairs, and it's processing key value pairs. You have a first phase that is a mapping phase where you partition the collection of key value pairs into what is called a split. Typically, a split will correspond to an HDFS block. Then you apply to each one of these input key value pairs a map function. Then you obtain intermediate key value pairs. And then you are arriving to the shuffling phase. And this is where we left last time, that at that phase, you might be producing a lot of intermediate key value pairs to a point that it might fill your memory completely. And what happens is you split it to disk, sort it. It's better because then you'll be able to read it efficiently to do the shuffling when the reduce nodes need them. So you split it to disk. And here, the idea, it might be overdoing it because the quantity of data might not be as big as for HBase and not as durable, right? But it's the same idea that whenever you split, you split something, you spill something to disk, you sort, and then you can compact. Once you have multiple files, you can compact them to larger and fewer files. But of course, this is all the local disk. We are not talking about HDFS here, right? So this is the first difference with HBase. It's the local disk of each one of the task trackers here. The second difference with HBase is that in HBase, when you store these, these log structures merge trees, it's for a very long time. This is the data that you have in your big table. So you keep it. And in MapReduce, that's temporary. It's only for the time of the shuffling, and when the job is completed, this goes away, right? So this is really just for the purpose of shuffling. But the idea here, I'm just making a link with HBase because the idea is more or less the same. So then you shuffle around. So you see this is what is quadratic because all the machines connect to all the machines. It's the reduce slots that connect to the map slots in order to get the data. So what happens is that the machines that are executing map tasks, they expose an HTTP server, and all the reduce slots can connect to that HTTP server and say, okay, I need these keys, or they request the hashes of the keys, and then since it's all sorted, it can be sent over. All right. A question that was asked last time is how do the reduce slots know which keys they have assigned? This is all decided centrally by the job tracker, right? So there are ways to do that. For example, you could take the hashes of the keys and you distribute the hash intervals to the slots, then they know exactly what they are responsible of. If you have a strategy that is based on intervals of key values, that's a bit tougher because you don't know in advance what the key values are, right? So this is why maybe a hash makes more sense. And then, of course, when the reduce slots know exactly what they are responsible for, then they know exactly what to request from the map slots. And since the map slots, when they spilled it to disk, sorted the whole thing, then they can retrieve the key values that they need to send. Yes?
Can you?
There you go.
Does it work? Yes. Oh. So having that the data is put to disk and it's not going through HDFS, I assume that if the machine dies, then also the intermediary result or the shuffling result is lost as well, right?
Yep. So we can talk a bit about that. So what happens if something goes wrong? What happens if one of the map slots, the machine dies? Then yes, you lose the intermediate data. This is clear. So if that happens, you basically need to re-execute the map tasks. So what's going to happen is that another machine is going from scratch to recompute the intermediate key value pairs, but only for the inputs that was crashed, right? Not for everything. So this is what happens if you haven't started you haven't started the reducing part yet, and you still didn't throw away on the other machines the intermediate data, right? In that case, you just recompute what you actually need. There can be problems arising if it happens later. Because imagine you already started the reduce phase and you already started reducing and you got rid of the intermediate data, then you need to start from scratch, right? So every time you need to ask yourself, it really depends where it fails and how it fails. There are the cases that if it fails, it's very local and you just recompute a small part. And there are cases where if you threw away the intermediate data and you were reducing, then you need everything again because you lost what you need to create that output. So the earlier it is, the safer you are, or the less the consequences are if something fails. Does it make sense? Yep. All right. And the reason why we lose it is that it's on the local machine. So this is why it's not in HDFS, so it's not replicated anywhere else. All right. But it's okay because it's temporary anyway, right? So it's not like you lose data because you still have the input, you still have the map function. So, you just recover it. Okay. All right. So we get the key value pairs over HTTP. And then the reduce phase is going to start, and then the reduce slots are going to run the computations of the reduce function on the intermediate pairs they received. Then they write everything back to HDFS. And what's going to happen here, what is important to understand is that every reduce task is going to lead to one file in HDFS, one file. So this is why you typically see these directory structures where you have a directory and then part 1, part 2. So here I simplified. Usually it's part 00001, and then you can increase all the way to 10,000 or 5 digits. So every task gives you one such file in here. And this is the reason why once you have written it back, it's very likely somebody else is going to read that again and do more analysis on that. That's the reason why you need to make sure that this can also be the input when you have plenty of files in the same directory, that this also can be an input to MapReduce. So it means that MapReduce can process the data from a single big file, but it's also able to process the data from all the files within a directory, because that might have been the output of a previous job. For whom is that clear? Okay. So this is a very common pattern that we have. And these are called shards. Usually we call these files shards. And of course, these files can be large enough that they are made of several HDFS blocks, right? So this is then a physical HDFS. Okay. Now I wanted to tell you a bit about the formats for input and output, because there's many ways that many places you can read from, many places you can write to. It's very modular, actually. So on the very high level, you can either be reading from and writing to a file system, actual files, or you might be reading from or writing to tables. So tables that can be relational or that can be H-based, right? So there's the two possibilities. It might be you have some, it's called the connector, typically when you connect a new backend that you can read from. So it can be a relational database management system that is kind of MapReduce friendly, right? That is able to expose the data in partitions. You have HBase that is, of course, very MapReduce friendly because it's the same, it's Hadoop, right? Hadoop has MapReduce, HBase, so they are designed to work together. And as you can imagine with HBase, what is going to be used as a split in HBase? A region, yeah, exactly. Yeah, so that's going to be the regions. And you might remember the scan operator, and the scan does exactly that. It scans through a region in order to get all the data that is in there. You can even select, project to a specific subset if you don't need all of the columns. Okay, so now the problem we have here is that these are not key-value pairs. These are tables. But MapReduce only ever knows about key-value pairs, doesn't know anything else than key-value pairs. So we need to force that into key-value pairs. It's actually quite natural, because in the case of a relational database management system, if you read from a table, it's likely you have a primary key made of one or more columns. So then the primary key is the key, and then the rest of the columns is the pair. And you can probably serialize this as text or as binary, and then you can transmit that as key-value pairs. For whom is that natural, that a table can be viewed in that way as a collection of key-value pairs? All right, perfect. And this is assuming the system is able to partition things, right? It's typically the job of the implementer of the relational database system of whatever technology it is to provide the connector to MapReduce and to Spark, right? And then they have, it takes work, you know, it's not something that comes for free. They have to design the thing in such a way that it interacts. Okay, so these are the tables. And the same in HBase, the key is the row ID, and then the rest, all the projection to the columns you want is the value. Okay, then let's look at the files then. We also have the same problem because files are files, right? And we need to have collections of key values. So there are several kinds of files that we are going to look at. There's text. Some files are text. Some other files can be directly actually in a key value format that actually exists. And there is even a native format called a sequence file that is often used by MapReduce, Hadoop MapReduce. Okay, so let's take an example of some text. Imagine that it's just really text, like a book, like Sherlock Holmes or whatever. And we need to transform that to key value pairs. It's very natural when you have text to use the new lines to do the cuts. So every line will give you a key value pair. This is very, very common. So the new line separators give you the separation in terms of the items you're manipulating, the key value. So each line is going to give you a key value. The \n character is separating. Okay, but the problem is we still need a key and a value. So what do we do? So the value, we're typically going to take the line itself. That's going to be the value. And for the key, what is done is that this here is going to be an integer that is the offset from the start of the file. So here it's offset 0. Then you have 18 characters. So the offset here is 18. All the way, then it's 27. So you basically pass the offset as a key and then the value. So it means that when MapReduce is going to process that, it's going to know the text itself, but it's also going to have in the key the information of the where it was located in the file, right? Okay. It can also ignore it, of course, if it doesn't need it. Do we have a question in the chat? No, I think it was just Zoom that was acting up. Okay. There is also a slight variation of that, where instead of splitting line by line, we do it in multiple lines. So for example, we could say 2 lines at a time, 3 lines at a time, and so on. And in that case, it's the same idea, but you only cut every other line instead of every single line, okay? Then there is another format that you might have. It might be that whoever produced that text file already intentionally made it in key value pairs. And what is typically done is that there's going to be a special character that can be anything that is the key value separator. It can be a tab, can be a semicolon, can be a comma, can be a space. You know, here I just used some Unicode character that is just this black circle. This is what you get. Then everything that's on the left of that character is the key. Then it's just going to be text. The key is text. And what is on the right side is the value. And of course, as always, you need to treat the corner case of what happens if this character is not there. And then in that case, it just goes to the key, right? But it's very likely, I mean, it's a corner case. In practice, I assume that if somebody made the extra effort of outputting some data in the form of key values in that way, that they will make sure that this character is every on every line and exactly once on every line, right? So this corner case is really more to avoid crashing, but I don't think it's a good idea to actually to produce files like that would have absent separators. Okay, and then we have the sequence files, which is binary, so it's efficient because it compresses more. It's not going to be in a text format, and it's very similar to the idea of H files in the sense that it just has key values, but the difference is that unlike H files, it's not necessarily sorted in the same way, right? So it's just another format for storing key values. I'm not going to go in details because a lot of the details actually might be similar in the sense that you need to store the key length and the value length in whatever order that is, and the key and the value so that you know how long they are, okay? All right, so this is the various formats that you can have. So let's do a few examples now. Let's have fun with a few examples. Imagine that we have petabytes of text, and we would like to count the number of occurrences on each word. That might be familiar to those of you who visited information retrieval last semester. So we are going to use MapReduce, and I want to know for every word, how many times does it appear in this petabyte of data? So first, we read that as key value pairs. We need, as for every job, a map function and a reduce function. Does anybody have any idea about the map function? What could we do? We need to count the words, the number of occurrences. Yes, over there. Oh, it's a. Thank you.
So maybe the map function can be for each word, create a key value pair where the key is the word and the value is always 1.
Yep, exactly. Very good. So this is exactly how you would design your mapping function. So you see this is done here. So we have lorem1, ipsum1, $1. By the way, this you might have seen this text. It's some filler that you see in all publishing software when you need to see how it looks like with text. It's just always the same. So I just did that. So lorem1, ipsum1, $1, and you see every time you just put it with 1. So this is the map function. What about the reduce function? Yes?
Sorry, I have a question. Would it already add up similar words during the map phase?
That is a very good question, and I have a cliffhanger for that because that comes later. This is a very good question. This is indeed an optimization. We actually did that for the Pokemons last week. The name that your ID has is called combine. You're basically combining, and you basically output less intermediate key value pairs because you pre-compute things. Does it mean that you know the reduce function if you do that? That you have an idea of what the reduce function is going to look like?
Just like counting the number of occurrences per word.
Yeah, exactly. So you basically do the counts, right? Everything that has the same key, you do a count. Okay, what if you use your optimization? Do you still do a count? If you can, because here it's only ones, right? But with your optimization, if there's several times the same word on the same line, then it's not going to be a 1. It's going to be a 2 or a 3. So how do you reduce then? Or anybody else who knows? Yes, over there? The sum, exactly. So you do the sum. You could do the count if you have only ones, and you do a sum if you do the optimization that you suggest. Okay, so here this is the reduce. It's either a count or a sum because here we didn't combine, we didn't optimize. So we have here lorem7. So you see always the same key here. All of these key values here, the intermediate key values, all of those with that key, and exactly those with that key are reduced to an output key value pair with the key and the sum or the count. Okay, what about filtering line? Now I would like to only output the lines that contain a specific word or that fulfill a specific predicate. So the same, I take my text. That could be actually, let's call it a brute force information retrieval query, right? You want to find, you look for a word, you didn't bother to build an index, a standard inverted index. You want to brute force search your way through the data sets. So you take this key value. The map function is actually just going to be a yes/no thing. So it's going to either output each key value pair the way it is, if it contains the word, or it's going to output nothing if the input key value pair didn't contain the word, right? So it's really a yes/no, it's a yes/no thing. It's even called the Maxwell demon, I think, with the physicists. Either you let the key value pair pass or you don't let it pass if it doesn't fulfill the predicate. The predicate is up to you. That's whatever you want to search for, right? So it's just a predicate that tells you yes or no. You take it, you leave it. And what does the reduce do? Well, it's the identity function, right? And this is actually very common in MapReduce, that either the map function or the reduce function is going to be trivial. In that case, the reduce function is trivial. It's just outputting the intermediate key value as it is without any modification, okay? Who understand that this is going to do the trick of filtering the lines? Okay. Now let's link it to relational algebra. What could it be used for in the relational algebra? What could we implement in the relational algebra? Imagine that these are not lines of text, but records or tuples. What is the relational algebra operator that would be implemented in that way? Anybody? On Zoom, maybe? Oh, yes, I see over there. We have the catch box. It's almost an athletics championship here now. Okay, go ahead.
Selection.
Selection, yes, exactly. That's a selection. What we've just done here is we've implemented a selection. This is it. And here you probably see it coming, that the MapReduce actually gives you a basis on top of which we're going to implement everything. Selection, projection, grouping, everything. So here we have the selection. Okay, let's do projection then. Let's go ahead. How do we project? So here I have to make the precision that MapReduce doesn't know anything about the input. It's just key value pairs to it. So the only way we project is because we as the user are kind of aware of what the data is. So imagine I have JSON in there. MapReduce couldn't care less that it's JSON. For MapReduce, it's just text. So it's parsing it in that way with the offset. So here we have the number of the line instead of the offset, but it's just a matter of convention. Okay, so now if I want to project, then this is going to go in my map function. My map function is going to take every single key value, which is a JSON object. It's going to project, so it's going to only keep some of the keys and throw away others. So here we keep ID and country, and we throw away A, and we project. What is the reduce function? Identity, exactly. Again, the reduce function is trivial and is the identity. We have just implemented the projection. You see how easy this is? We have the selection, we have the projection. You probably understand the group by, because in essence, MapReduce is a group by, right? What you do when you shuffle around and then reduce, you are actually executing a group by. Who understands that? That it's basically a group by. It's an aggregation. Okay, very good. But we'll come back to that, because today we are focusing on MapReduce, but the whole thing with manipulating with a query language and the whole relational algebra, that will come in a few weeks. That will slowly add back on top of that. But I hope it's an appetizer for you of what's coming, what's the way you can actually get the query language on top, thanks to MapReduce and similar things. Okay, now optimization. So actually, you kind of explained it, right? It's your colleague here who told us. Indeed, it is something generic that when you have, so you have map, then shuffle, then reduce. So you have the mapping phase and the reducer in the reduce phase. I didn't realize, because I will make very clear you should never say mapper and reducer, and I don't know why it's still there. I will remove it from that slide. Map phase, reduce phase. Forget about mapper reducer. So we have the map phase and the reduce phase, and indeed we can reduce the amount of data that gets shuffled around. And with reduce, it's not the reduce in the sense of MapReduce, but really just squeeze the amount of data shuffled around. And the key here is to add an intermediate level here that during the map phase, you can combine some of the intermediate key value pairs, you can combine them into less intermediate key value pairs, right? And the moment that this happens is typically when you when you flush to disk or when you compact. This is the moment to do that. You might have accumulated key value pairs in memory, and when you flush to disk, you apply this combined function in order to squeeze the number of key value pairs into less, and then you store less on this, so you can fit even more, right? So the quantity of data you can process is bigger because you're constrained by the size of the hard drive, right? If you exceed the hard drive, you have a big problem. Okay, so when flushing, when compacting, and maybe you could also imagine that you regularly sweep the memory and also apply it on the fly, right? This is also something that is done in HBase. All right, so that's the combine function. Now comes the question, what is that combine function, right? What do we use? Because we have the map function, the reduce function. Now we need a combine function. Well, it's actually easy in 80% of the cases, because in 80% of the cases, the combine function is just the same as the reduce function. However, it only works under specific conditions. Who can try to guess under what conditions on the reduce function we can reuse that reduce function as the combine function and optimize in this way? Any idea what we would like for the reduce function to be like? I see several raised hands, maybe over there.
That intermediate data and output data have to be of the same kind.
Yep, absolutely. That is the first assumption, because I told you that in general, you have a specific type of input, specific type of intermediate values, key values, and a specific type of output. We need indeed that the type of the intermediate key value pairs is the same as that of the output key value pair. So if it's integer date values, then it must be integer date values also on both sides, intermediate and outputs. Something else? Yes?
The reduce function has to be idempotent if you want to use it as a combine function as well, such that no matter how many times we apply it, it doesn't change the actual output.
Oh, that's interesting. Idempotent, right?
Yes.
It might be. So I had two other properties in mind. I think more about that, about this, whether idempotent. I think more about that. You said homomorphic, right? Homomorphic. Yeah, I'll investigate that. You know, when I'm live in front of an audience, I think slower. So I'll get back to you on that. The two words that I had in mind, and they might actually imply homomorphic, is commutative and associative. So here, this is your answer, right? The same type for the output and the intermediate key value pairs. And here I have commutative and associative. So it shouldn't matter in what order you call the reduce. And it also shouldn't matter how you associate. So associative means you first reduce the first two keys and then you reduce the result with the third one, or you first reduce the second and third one and then combine the first one with the result. So commutative and associative. Do you think that it implies homomorphic? Okay. Yeah, because that's a good point. I just didn't think about that. So I'll investigate offline and I'll come back to you on that, on this additional property. Yeah. Okay. Okay. So if we have this, then we can use the reduce function also as the combine function, and that's just going to work. And the idea with this optimization is that we bring the query to the data. This is something very, very, very general. When you do large-scale analytics, your goal for performance is to squeeze at all levels in order to have as little data flowing around as possible. This is called pushing down, push down, and you try to very early compress the data and eliminate data that you will not need later. So this is very generic. So in the case, for example, of counting words, the reduce function was a count. Count, I think, is not associative. So that wouldn't work. So we need the sum. So if you use the sum here on this, then you can use it as the combined function. Here's how it works. So you see, here you just reduce directly. If you have the combined function, you say 1 + 1 + 1 gives you 3, 1 + 1 + 1 + 1 gives you 4. So this is the combined function call. And then what happens is that already on the map slot, you throw that away. And this is what you actually keep. And this is what you get shuffled around, right? So you can see that we have less data going over the network. And this is great because this is one of the bottlenecks, right? So where you ship the data over the network. So you combine, and then you do the sum again. You see it doesn't change the result. 3 plus 4 gives you 7. It's both commutative and associative. For whom is that clear? That when you sum, you basically just sum intermediate results. That's basically what you do. Okay. Now, a few words on the APIs. There are several APIs to MapReduce. So it's implemented in Java. So there's a Java API that I'm going to show to you. But there's also another API called streaming. It works a little bit like standard in, standard out on the command line, a bit like grep style. But anyway, let's look in Java the way that it looks like. You will see it's very natural, actually. The map function is defined in a class that's called mapper. It's the name of a Java class. That's the only place where we should use that word mapper as the name of a class. So my own mapper implements a function, and you see I map a key and a value, always a key and a value, one at a time. And then I can produce with whatever code I want to write new keys and new values. And then I can call context write as many times as I want in order to create my intermediate key value pairs. If it's just 1, you call it once. If it's 0, you don't call it at all. And you can call it multiple times for several intermediate values. Reduce is slightly different because here you have a key that belongs to the group that you reduce together, but the values come as a list of values. So it's convenient to just only require that it's iterable. So you just stream your way through it, right? Next. So you go through the values associated with that key. And here you save a bit of space. You don't repeat the key, right? It's the same one for all the key values in that group. So you iterate through the values, and then you produce a new key and a new value. Very often, the new key will be the same as the key, actually. And then you call context write also to write your output, right? So it should be pretty straightforward. It's just the way it works in Java. And then you have this for the job. It's typically in the static void main. For those who know Java, where it goes, you say, okay, this is my map function. This is my reduce function. Give them as classes. So my own mapper, my own reducer. You say where your input is. So you specify all the paths of the file that you want to see as inputs. Then you set the output path. This is where you want to write. Is it going to be on HDFS? Is it going to be in HBase? You know, just need to say where you write it back. And then you wait for it to complete. Okay. If you want to combiner, it's easy. You just also set it. And in many cases, you just reuse the reducer class because that's just the same, right? If it's fulfilling the properties that you can reuse it, okay? Okay, so what about the input formats? We actually kind of look into it, but basically you can read from a relational database management system with DB input format. You can read from HBase with table input format. You can read from key value files with the separator in the middle, from text, from sequence files, and so on and so on. And the same goes for the output. You can output back to a relational database, to HBase, to sequence files, to text, and so on, right? So this is what you use here, basically, in order to set your format. So you just pick. It's a restaurant menu. You pick from what you want in there, and you choose what you want to write back. Okay. Now, I would like to make a very, and I cannot emphasize enough how very important that very is, a parenthesis on the terminology, because the internet is full of people who just say mapper and reducer. It's a very bad idea to say mapper and reducer because it blurs everything and you don't really know what's happening anymore. I would like you to really avoid using the term mapper and reducer, except maybe for the name of the classes in Java, and instead call them slots, tasks, functions. So I will explain to you exactly. And hopefully the slides that follow will give you a clarity of mind on what's going on in MapReduce on a more precise level. And you will see, hopefully, why it's a very bad idea to say mapper and reducer, because it hides this level of precision. Okay, so instead of mapper, you might actually mean map function. The map function takes a key value and outputs 0, 1 or more key values. The reduce function, some people call it reducer, it should say reduce function, takes some key values that have the same key and outputs 0, 1 or more key values. The combine function, some people say combiner, it's even more horrible to say combiner, you will understand why soon. It's a combined function that, just like the reduce function, takes key value pairs with the same key and outputs 0, 1 or more, typically 1, but 0, 1 or more key value pairs. Okay. Now, some people say mapper, but they might not mean map function. They might mean map task. What is a map task? It's like an assignment. It's like homework, right? It's a task, it's a recipe. It's an assignment that basically consists of evaluating the map function on a specific split of the input. This is called the task. Every split gives you one map task. What is it about, this task? It's about calling the map function on every single key value that there is in your split. Sequentially, there is no parallelism there. Sequentially, you start with the first one, then the second one, then the third one. It's an iteration, sequentially, one by one, and then you produce your intermediate key value pairs in that way. This is a map task. A map task is not a computer resource. It's really just a to-do. It's an assignment, right? Okay. Then you have the reduce task. It's the same thing. A reduce task consists in a sequential call of the reduce function on groups of key value pairs within whatever the current responsibility is as assigned by the job tracker, right? So you have some partition of the intermediate key value pairs, and that partition has plenty of groups of key values, and you call the reduce function on each one of them sequentially. That is a reduce task. And there are as many reduce tasks as there are partitions of the intermediate data. Combined task, this is why when people say combiner, it can be very confusing. That does not exist. Combined task does not exist. A combine is just about calling a function when you flush and when you compact. That's all it is. It's just an optimization, but there is no such thing as a combined task. Okay. Now, when people say mapper, maybe they don't mean map function. Maybe they do not mean map task. Maybe they mean map slot. The map slot is a computer resource that is responsible for executing map tasks. So a slot is basically one task at a time. It takes one task, so map task 1, for example, then it sequentially goes through the calls, maybe flushes it to disk and so on. Then it's done with the task, okay? Then it does a second task. Second task, again, sequentially calling, produces intermediate key value pairs, done. Then you might have a third task, and again, sequentially. All of that is sequential. It's sequential within the task, and it's sequential across the tasks. No parallelism at all within a slot. This is a map slot. Slot, think CPU and memory, computer resources. It's like the difference between a baker and the recipe to make bread, right? The task is the recipe to make bread, or the assignment to make bread. The slot is the baker, okay? The reduce slot is the same. It's just a slot, CPU memory, that executes reduce tasks by sequentially calling the reduce function. And the tasks are sequential. You never have several tasks at the same time in the same slot. It's sequential. And combined slot doesn't exist. That's also a reason why not to say combiner. There are no such thing as combined slots. Okay, now, when people say mapper, they might mean the map phase. That's the mistake I made earlier that I will immediately remove after the lecture. A map phase consists of multiple map slots all over your cluster, maybe 1,000 map slots, 1,000 CPU cores with plenty of memory that execute their map tasks. Now this is in parallel because every one of these cores on your cluster is going to execute these map tasks in parallel. So you see, all you need to do when you do MapReduce at the map phase, you have, let's say, in that case, you have 9 splits, so 9 tasks, and you just spread over these tasks all over the slots, right? Every task goes on one slot. Why does this slot have more tasks and this one only 2? Well, because this one was slower, right? So this one was quicker, it finished earlier, so it got more tasks, right? So you just give the task as long as they remain, and then at the end, you just wait idly for everybody to finish. For whom is that clear? Okay. So what's very important, map function, map task, map slot, and map phase. There is no parallelism within a task. There is no parallelism within a slot. There is parallelism across the slots. The magic happens because we have plenty of slots that can do it in parallel. It's like having a bakery with 3 bakers, and the 3 bakers can just in parallel prepare the bread, but each baker can only do one, except maybe if they are very good and they can even multitask, but a baker can do only one thing at the same time. Okay, the same for reduce. You have reduce slots in the second phase, in the reduce phase, and they just get the task and you just spread them evenly over the cluster as long as there remain tasks. And when there's no more tasks, they just wait idly, right? So this is dynamic. You see the one on the right was slower, so it only got 1 task, and then the first 2 finished earlier, and so they got the task 4 and task 5. Okay, combined phase, no such thing. That doesn't exist. All you have is a combined function during the map phase. So you see, this is a summary of everything. You have tasks that are sequential function calls, slots that are sequential tasks, and then the parallelism is across the slots, right? So basically in MapReduce, to statically allocate the slots. So before it starts, you already say this core is doing mapping, this core is doing reducing. This is decided before, and so you already know in advance what each CPU core is going to do, either mapping or reducing. Okay, maybe it's time for a break. Maybe you do you want to ask your question, then we go for a break, or? Okay, so let's do it right after the break. So you deserve the break, right? So let's meet again at 1/4 as always. Enjoy your break. Welcome back. So I have explained to you the difference between functions, tasks, slots, phases, and hopefully now you know that you shouldn't be saying mapper or reducer, and that you should be saying map task, map slot, map function, map phase, right? Do we have a question over there? Oh, no, no worries. All right. So, oh, because there was noise. Oh, sorry. no worries at all. All right. So, what you need to do, so what I was finishing on, is you assign the slots, meaning the CPU cores and the memory, to either mapping or reducing statically before the job starts, and you already know in advance who is doing the mapping, who is doing the reducing. That's MapReduce version 1. I wanted to add something because I had a question in the break on this notion of slots, of what is exactly a slot. And a slot, you could think of it as a thread. It's a thread on the machine. So if you have a machine that has 16 cores, maybe you can have 32 threads, right, with hyper-threading. So imagine that on each machine, you have multiple threads, and each one of these threads is a slot. You know that a thread is sequential, right? In a single thread, it's sequential, so you do one task, and then one task, and then one task, and you have plenty of threads on the same machine, then you process the tasks in parallel. Okay, is it all clear? Who is with me on that? Right, so now nobody will ever say mapper and reducer ever again. And when you see on the internet that people say mapper and reducer, then you should be able to think, okay, do they mean function? Do they mean task? Do they mean slot? Or do they mean phase? And then you have a clear mind, and there's nothing better than a clear mind to understand technologies. Now, I have a last thing that I wanted to finish on, which is one of the tricky points. So I'm very impressed this year on how many of you managed to bring up questions that basically anticipate on what's to come. And it happens more than in other years, which is absolutely awesome. Like today, for example, with the combining. But I didn't hear anybody about these tricky points, about an impedance mismatch between blocks and splits, because there is something that should itch you a bit here. Because I told you, a task can be a map task or reduce task, and a task, basically, if you look at on the map face, each one of these tasks corresponds to a split, right? You have this split right there, which is this task, this split right there, which is this task, then the tasks get executed on slots. So every task corresponds to one split. The splits, I told you, are more or less HDFS blocks, right? Because you want to be efficient, it's implemented together with HDFS. So what's going to happen is that every time you have a block, you read the block that gives you a split, and then you execute the task. So every time that a map slot needs to read data, ideally it's going to short circuit even on the same machine if the block is on the same machine as the map slot, and that's it. Or is that it? Well, no, that's not it, because we have here a problem. Is that blocks in HDFS are about bits. It's 128 megabytes exactly, and then it cuts. Then it's the next block. HDFS doesn't know and doesn't care about what these bits are. These are just bits. But on the logical level, this is MapReduce, these are the splits. What is a split? It's a subset, it's a partition of the collection of key value pairs. So the splits are full key value pairs. It's not half of a key value pair and then the other half is in another split. That's not how it works, right? So you must have full records, full key value pairs. So now you understand that if you have the case that at the very end of a block, you have the very last key value pair over there that is cut because of the way that HDFS blocks work and it continues on the next block, then you have a problem. That means that a split is kind of sort of an HDFS block, but it's not exactly an HDFS block. There is this tiny little bit of impedance mismatch in there. So how is it solved? It means that imagine that you were optimizing things and then you short circuit, just like in HBase, that whichever slot was responsible for this split happens to be on the same machine as this block is stored. So there's a replica on this block on the same machine. So that's easy. It was read directly from the disk. But you might have to do a remote read to another machine if the next block here is not sitting on the same machine. So then you need over the network to have these extra bits to finish the key value pair that you had here. And this is why HDFS actually allows you to read a block partially, because you don't want to trigger shipping over the entire block there. That's the last thing you want. You only want the few bits that you need for your last key value pair. So this is the motivation why in HDFS you can read a partial block, just a specific subset of a block. Okay, and what happens? Of course, it happens all the time, right? What are the odds that a key value finishes exactly at the end of a block? Maybe happens every 1,000 blocks, right? That's very rare. So most of the time you're going to have that, and this is all handled by, of course, the implementation of MapReduce that's going to take care of all of that for you. But I just wanted to make you aware. This again has to do with data independence, that we have a physical level with the blocks of HDFS, and we have, from the perspective of MapReduce, a logical level where you think in terms of collections of key value pairs, right? For whom is that clear? Okay, this in fact concludes the lecture on MapReduce. Told you everything that I know on MapReduce. Yes, we have a question?
I hope it's not a stupid question, but I thought with HDFS, when we have a file that it's made up of multiple blocks, the first replica is stored on the same machine.
Yeah.
Or the first replica of each block that makes up that file.
Yeah.
So how come then if a key value doesn't finish in this block, isn't the next block anyway going to be on this machine? Or is it just due to the actual, let's say, balancing that happens over time and such that this may happen?
This is a good question. I think you were probably assuming that here this was the first replica. You know, because here this can be any replica, right? In HDFS, the blocks, they don't have an order of the replicas. So it is true that the entire file, if it fits, of course, if it doesn't, then it's not possible, but there will be a copy of the replica of each blocks on the same machine. But if you want to execute MapReduce, a MapReduce job on that file, the last thing you want is take the first replica on the same machine, right? Because you cannot fit. What you are going to end up doing is that everybody is going to connect remotely to the same machine. So you have a bottleneck. So what's going to happen if you want to do MapReduce is that you're not going to use this first replica. I'm saying first replica with quotes because, again, there's no notion of first replica. What I mean with first replica is whatever replica got written on the same machine as the client. So what happens instead is that you are going to look at the quote second, quote third publicas, not publicas, replicas. So these here are really spread all over the clusters and might have been the second and third replicas read. And this is why, so you have a remote read, because then the second replica might have been written to a different machine than this one. Yeah. Does it make sense? Yeah, but it's really good because this is the kind of questions that make you think about what's going on in the cluster and how HDFS and MapReduce interact. Any other questions? Okay. Who is comfortable with MapReduce? Who feels like you could explain MapReduce, let's say, to third-year bachelor students? Okay, very good. So you have exercises, of course, to use MapReduce. Okay. All right, so I'm going to stop the recording here, and then I'm going to start a new recording with the next set of slides. So see you on the other slides.